I'm just going to write down an equation. Y is equal to VT plus 1/2 AT squared. Okay? We will see this. This is a kinematics equation. Y is a position. And if Y is a position, it's likely to be in meters. Velocity is going to be in meters per second. It's going to be a speed, so velocity is in meters per second. Acceleration is in meters per second squared. And so if I look at this, I get Y is in meters. And if I'm doing this, I'm going to have my meters per second times time. And then I have my 1/2. And then I get meters per second squared. And I've got time squared. So I end up with meters and meters. Remember, I can only add like units. So if I'm adding things, I've got to have meters and meters. I can't have something. And if I've written my equation down wrong, let's say I put it in my cheat sheet and I write it down wrong like this will end up giving me meters, and this gives me meters per second. Obviously, I've done something incorrect. That is not a correct equation. So doing dimensional analysis is going to actually help you make sure that you've got things in the right spot. It also is going to help you a lot of times when we're dealing with stuff like this. So let's use density. All right, so I've got density. Density is going to be mass per unit volume. And let's say I get into a hurry, right? I get into a hurry and I'm going to do density divided by volume, and I'm going to say that that equals mass because I got into a hurry and I got sloppy, or I wrote it down wrong, or I was tired, and I get this. So density is in kilograms per meters cubed, and if I divide that by volume, this is meters, oops, ugly. This becomes meters cubed. This gives me some kind of unit that looks like kilograms, meters to the 6th. Well, guess what? That is not equal to a mass. So obviously I've done some arithmetic incorrectly to get that. So when I'm using I can use my dimensional analysis to really help make sure that I manipulate the equation correctly. Did I do something correctly? Am I getting the right units that I want to have? So that's going to help you out a lot. All right? It's going to help us out a lot. Then we have conversion factors. So I'm going to come back to that one. Come back to that here. We're going to do some conversion factors because this first chapter does conversions. And we have to, so I've got a crack in the wall. And it has been growing at a rate of 0.25 inches per year. What is this in millimeters per, I'm going to do it per hour, sorry. We're going to do it in millimeters per hour. Do it in millimeters per hour. Now, there are some conversion factors that you should have ingrained into your head. Okay? Some of them you just gotta know. And not everybody's are the same, but one of the ones that everybody should know off the top of your head, because it's a perfect, 1 inch is equal to 2.54 centimeters. And there are 10 millimeters in 1 centimeter. okay? 2.54 inches per centimeter, or 2.54 centimeters is equal to 1 inch. And I got 10 millimeters into a centimeter, which is why we like the metric system, because I can do all these conversions all the time. All right? And also, if you want to get a refresher, because you probably haven't used them in a while. All right? Probably haven't used them in a while. We just did this calculation. My son called to ask to verify his math because it didn't sound right to him, so he wanted to do it. So we had 300 nanoliters, okay, 300 nanoliters, and we had 100 microliters. And I wanted to do the conversion factor. So I'm going to do this real quick because I want to show you that 300 nanoliters is going to be 10 to the minus 9. And 100 microliters is going to be 10 to the minus 6. And so these are now both in liters, so that's nice. Okay? But remember how you handle exponents. Okay? If I'm doing this, my answer now is 3 times 10 to the minus 3 liters. Because of how I can handle those exponents. So when we're dealing with the metric system, there are nice ways to do shortcuts. Okay? Nice ways to do shortcuts. I don't even have to put those into my calculator in order to get to that to get there right away. So you may want to kind of review using exponents because it shortcuts a few things. And if anybody wants to know, he was getting ready to do some PCR dilutions, and so we were working in nanoliters and microliters. Real tiny stuff. All right, so we want to get that. So I'm going to start with my 0.25 inches per year. All right, and I want to end up in hours, so I'm going to do my conversion factors, right? So there's going to be 1 year, so I'm going to cancel out my years. There's going to be 365 days. And 1 day is 24 hours. So when I do that calculation, if I were to do that right now, I'd end up in inches per hour. But I'm going to go ahead and continue my conversion. So I want my 2.54 centimeters per 1 inch. And then I've got my I've got 10 millimeters is equal to 1 centimeter. And if I plug that into the calculator, I'm going to get 0.0000725 millimeters per hour. Okay, couple things, folks. Since it's probably the first time I've actually encountered it here, I use what's referred to as a Latin 7. And I use what is referred to as a Latin Z a lot, where I will put the dash mark in there. Because what happens is that a 7 or a 2? Or is it a squiggle on the page?
Question mark.
It could be a question mark even. So in order to help clarify what that number is, partially because I lived in Panama for 4 years and the Latin 7 was very common in Panama, it also is very, very helpful to distinguish so we're not getting sloppy and everybody understands that that's a 7. So it's that I will use that for my numbers. Your text and several other texts now will do this. So I've got 100,000 here. They'll leave a space. I don't like to use the space. I like to go ahead and keep my commas in there. So I keep that, and I generally always put a leading 0 in front of my decimal point, because you see my paper here, it's already got specs. If I write a number like here, is that 135 or is that 0.135? Because I have a spec on my paper, you guys won't necessarily know that. So I generally use the leading 0 to show you that that should be 0.135. Because what's going to happen to you folks is, as you start putting things together, your calculations and everything else have got to be clearly communicating. Yes, I know people's handwriting is a little difficult and different, and you will also notice that I use a mix of cursive and print. I still print most of the time, but we do have a bit of both. And I know that there are some places now that looking at cursive is going by the wayside. So be aware that those things that are out there. So hopefully most of you don't have any trouble with conversions. But, you know, every first physics chapter refers back to conversions, so we'll do one. I've got a pizza. Has an area of 36 inches squared. What is the radius? And the area in centimeters squared. Okay, there is no rhyme or reason as to why you do one or the other. I'm going to start with centimeters squared because it's easier. And we've just been talking about it. So I got 36 inches squared. And we know that 1 inch is equal to 2.54 centimeters. I've got to make sure that I square it in order to get my units to come up correctly. So if I do that, I end up with 232 centimeters squared. Area of a circle is pi r squared. So if we have this, so that's going to equal 36 inches squared. So r squared is going to be 36 divided by pi inches squared. R will end up being 8.6. No, sorry. What's the radius and the area? So if I do my 36 divided by pi. 36 divided by pi ends up being 11.5 inches squared if I do the square root.
Didn't you just read you already got your centimeter squared, that's 232 centimeters squared for the area?
That's for the area. 36 inches squared, 232 centimeters squared.
And whenever you're figuring out the radius in centimeters, you're doing the calculation there.
You can. I didn't specify units on the radius though.
What is the radius and the area in centimeters?
Well, I just said the area in centimeters squared. I asked what the radius is, so I didn't really specify. And I asked for the area in centimeters squared.
Well, the way the sentence read, what is the radius and area in centimeters cubed?
Now that's actually a square.
Or squared, I assume.
Okay, but radius can't be in squares.
But what I'm saying is the way the sentence, the way you wrote the sentence, what is the radius and area in centimeters? I would assume the radius, you wanted the radius and area in centimeters.
Well, we can do it that way too. I agree, I intended, and actually that's what I calculated in my notes, The radius is 8.6 centimeters. If I do it that way. So you're correct. You're correct. And what you'll find, and this is one of those things that's going to frustrate the heck out of you guys. It'll frustrate the heck out of you guys. It frustrates the heck out of me, and I even write my own notes, okay? Is I'll come in, I have my notes laid out, right? I have my notes all nice and laid out, and then I ask a different question. Well, if you ask a different question, you get a different answer. In this case, I didn't specify the units for radius. It is implied that maybe I wanted it in centimeters, just like you said. It's implied that I may have wanted it in centimeters, but I didn't specify. And I'll guarantee you if I did this on a test, you all would come back and say you didn't specify what that radius is in, so I gave it to you and whatever. And I have been mean, cruel, and wicked that way too. Even as a student, I was mean, cruel, and wicked that way. We had an instructor that drove us crazy. We loved him. And all of us went in and did it. And he asked to calculate the speed of something. And we gave it to him in leagues per fortnight. Well, he'd been harping on us about a few things, so we gave it to him in leagues per fortnight. We also gave him some volumes in hogsheads per, we gave him some volume flow rates in hogsheads per some weird unit, hogsheads per week or something like that. So, we did some really cool weird things. So you're absolutely correct. All right?
But what you're saying is don't do that to you.
Well, I'm just saying that I'll have to, we end up with it there. We end up with fun things like that. All right, so here comes a fun one. This is the human heart. The human heart pumps 5 liters of blood per minute. Okay, 5 liters of blood per minute. So we want to know how many liters is pumped per day. So we can do that calculation, right? So I got 5 liters per minute. We got 60 minutes per hour. And we have 24 lovely hours per day. And when I plug that into the calculator, I get 7,200 liters. Now, question is that reasonable? Well, first of all, think about 5 liters per minute. That's 2.5 2-liter bottles. Your heart is a pretty substantial pump, okay? Your heart is a pretty substantial pump. So the 7,200 liters actually makes a lot of sense. But the question now is, how big, just so that you guys can put it into your head, how big is 7,200 liters? So, let's put it into gallons. Well, 1 liter is approximately 0.26 gallons. So if I do that conversion, that works out to be 1872 gallons. It's a lot of milk, okay? Well, now I'm going to give you another reasonable thing, a standard American bathtub. And a standard American bathtub is approximately 80 gallons. A standard American bathtub is approximately 80 gallons. So think about that for a second. Your heart is going to pump about 23.5 bathtubs.
You can calculate how fast somebody would leak that.
Doesn't take long. And it's called a sanguination, by the way, the proper term, sanguination. That's why if you hit an artery that you gotta get it stopped quick, because you only really have about 8 liters of blood, right? Isn't that what the standard amount is? I don't know, somebody have to Google it, but I think 8, for whatever reason, 8 sticks in my head. All right, the last time I did this calculation, because I always do this one because it's always fun, because people don't understand exactly how much rain is 1 inch of rain. Okay? So this time last year, we actually had a rainstorm. I have an 11.4 acre plot of pasture out in Osage County. Actually, I have, between the 2 plots I have something like 52 acres roughly, okay? And when we talk about an inch of rain, you're talking about the amount of rain that will fill 1 inch across, so it's 1 inch deep. That's how rain is measured. So if we got 4.1 inches of rain, okay, if you get 4.1 inches of rain, how much water is that? It really is how much water is that. So I'm going to do 4.1 inches of rain on our 11 acre plot. And so 1 acre, just because people don't remember it, 1 acre is roughly 43,560 feet squared. Okay? 1 foot is 0.3048 meters. Okay? 1 foot is, and we already know that 1 inch is equal to 2.54 centimeters. Okay? So we can calculate the volume of that, right? So I'm going to take my 4.1 inches, that's 2.54 centimeters per inch. 2.54 times 4.1 gives me 10.4, and I'm just going to leave it to 3 significant figures, 10.4 centimeters. All right, so I've got 43, 50, or 60, and that's feet squared. And 1 foot is 0.3048 meters. So if I do that conversion right there, I got to square that. So 43,560 times 0.3048 squared is 4,046 meters squared. I got to convert this. There's 100 centimeters to 1 meter. So we want that. So I'm going to take my 10.4 divided by 100. So I've got my area times my height is going to be my 46 times 0.104. This gives me, oops. That gives me about 420 meters cubed. It's 420 meters cubed of water. And it turns out 1 meter cubed of water is 264 gallons.
Wow.
That is 110.87 gallons of water that fell in a 24-hour period. Now, when with the last hurricane that came through Houston, I actually calculated the number of Caw Lake volumes that fell in a 24-hour period. It's a lot of water.
How did you get from 420
Meters cubed,
to 110,000?
1 meter cubed of water is 264 gallons. And so you just multiply the 264 times the 420. Alrighty. We've gotten through estimates, conversions, we started looking at our trigonometry. That should get you pretty well into, through the first chapter. And we'll see everybody on Wednesday.
Like that, this